Okay, here we go with the 2-2 video solving two-step equations. After this lesson, I should be able to solve a two-step equation in one variable. Here we go. The diagram shows the amount of money that each player starts with in a video game. To be fair, each player should have the same amount of money. If each chest contains the same amount of money, how much money must be in each chest? How do you know? Well, if I look here, player 1 has 3 chests and 6 coins. And over here, player 2 has a whole bunch of coins over there. Alright, so my goal is to figure out how much has to be in each one of these chests, considering that they all have the same amount in them, so that the left side, the player 1 side, is equal to the player 2 side. So if I just set up a real basic table here for an equation, 3 chests plus the 5 plus the 1 has to equal 30. This is 30 over here, if you add them all up. So I have 3C, C standing for the amount in the chest, plus 6 is 30. And then I can just solve that little equation. So if I just chop a 6 off of both sides, I subtract the 6 to undo the addition, I'd wind up with 3C has to equal 24. So 3 times what number has to be 24? So if I follow my procedure from last time, 3 times C is 24. So in order to undo multiplication, I would do division, divide by 3, and I know that C is 8. So each chest is worth 8. And if you go and check it, you'd have 8, 8, and 8 was 24, plus 6 more should make 30, which is the same as that side. Okay, so to solve two-step equations, we can use properties of equality and inverse operations to form a series of simpler equivalent equations. We can use the properties of equality repeatedly to isolate the variable. So pretty much the same as last lesson. So here we go with a bunch of examples. What is the solution of 2x plus 3 equals 15? Well, if I take that equation, and again, I kind of like to separate that into a left side and a right side by drawing that vertical line. That just reminds me that whatever I do on the left, I have to do on the right. I'm trying to isolate the x's. So I'm going to get rid of that 3 first. So I would subtract 3 from both sides. Now I'd be left with 2x equals 12. And now 2x means 2 times x. So in order to undo the times, I would do a division. I divide both sides by 2, and I get x is equal to 6. 2 times 6, which is 12, plus 3 more, does make 15. So it all checks out. Alright, here's another one. Solution of 5 equals t divided by 2 plus minus 3. Okay, so here we go. The first thing I would do is I would multiply both of those equations by 2 because I don't like that denominator. So when I multiply everything by 2, I'd wind up with 10 equals t minus 6. Don't forget, you have to do it to all of the pieces. When I multiply by the denominator, all I'm left with is the numerator. So now I have a simpler equation right here to work with. Now I just got to get rid of this minus 6. So I would add a 6 to both sides, and I'd be down to t equals 16. Some people may ask, can I add the 3 first and then do my multiplication by 2? And that is certainly fine. I just like to try to do the multiplication in the beginning to get rid of that fraction and have that gone. Okay, so here's number 3. A little bit of a word problem. We are making a bulletin board to advertise community service opportunities in my town. You plan to use half a sheet of construction paper for each ad. You need 5 sheets of construction paper for the title banner. You have 18 sheets of construction paper. How many ads can we make? Well, what do we know? We know that each ad takes a half a sheet. We know that the banner itself is 5 sheets. And then I have 18 total sheets of paper. Well, a half a sheet times the number of ads plus the 5 sheets for the banner is going to give me a total of 18 sheets. Okay, so if we let A equal the number of ads, the equation would be 1/2 A plus the 5 sheets equals the 18 total sheets. Okay, so now I have the skills to solve that equation. Again, I would multiply both sides by 2 to start to get rid of that fraction as soon as possible. I'd have an A plus 10 equals 36. 5 times 2 was 10. 18 times 2 is 36. And now all I have to do is move this plus 10 by subtracting 10 on both sides, and I'd get A equals 26. so I can make 26 adds. If you wanted to, you certainly could subtract 5 from both sides and then multiply through by 2. That would be fine also. Okay, here's a slight adjustment to that problem. Suppose we use a quarter of a sheet of paper for each ad and 4 full sheets for the title banner. How many ads can we make if we have 18 sheets? All right, so the paper per ad would be a quarter of a sheet. I need 4 sheets for the banner, and I have the total paper of 18 sheets. So a quarter of a sheet times the number of ads plus the 4 sheets for the banner should equal a total of 18 sheets. Again, let's let A be the number of ads. So I have a quarter times A plus 4 is going to be equal to 18. All right, I'm going to multiply both sides by 4 to get rid of that fraction. And I'd wind up with simply A plus 16 equals 72. And then I would subtract 16 from both sides, and I'm going to get A equals 56. We can make 56 ads. So in these last couple examples, we've had some fractions that we've been getting rid of. So when one side of an equation is a fraction with more than one term in the numerator, we can still undo division by multiplying each side by the denominator. So we've seen a couple examples of that. We call that busting the fraction or fraction busting. Okay, so those are a couple names for the same thing. So here's an example, like those previous ones. Nice example here. So I have x minus 7 divided by 3 equals negative 12. So to me, I would multiply both sides by 3, and that'll get rid of the denominator. All I'm left with is x minus 7 equals negative 36. And now I have a simpler version of that same equation, and all I have to do is add 7, and I'd be x equals negative 29. So that fraction busting can really help you. Here's another example. So I have the 4 in the denominator, so I'm going to multiply both sides by the 4. And all I'd be left with is 24 equals x minus 2. Now all I have to do is add 2 to both sides, and I get x equals 26. Okay, so we take a tough-looking equation and we turn it into a much easier one by simply multiplying the whole thing by whatever's in the denominator. All right. When we use deductive reasoning, we should state our steps and our reason for each step using properties, definitions, or rules. So basically, if I was going to solve this equation, somebody should be able to follow along and see my steps. Okay? So it asks me for the solution to negative t plus 8 equals 3, and it wants me to justify each step. So here's the original problem. So I would just say that's the original equation or the given equation. And in order to solve that, I need to isolate the t. So I would subtract 8 from both sides. My new equation would be negative t equals negative 5. What did I do? I subtracted 8 from both sides. So there's my justification to get to that line. I don't want negative t. I want positive t. So I would have to divide or multiply even both sides by negative 1. And I'd wind up with simply t equals positive 5. And what did I do to get there? I divided both sides by negative 1. Okay, so there's my justification for each step. One more look at an example like that. I got x over 3 minus 5 equals 4. And they want me to justify each step. So again, I always like to split that thing in half. Remind myself whatever I do on the left side of the fence, I got to do on the right side of the fence. There's my given equation. I'm going to add 5 to both sides. And I'd wind up with x over 3 equals 9. I added 5 to both sides to get there. I'm going to multiply both sides by 3, and I would get x equals 27. What did I do to get there? I multiplied both sides by 3. So you can see it with the little notation here, but we'd also like to see it in the justification side of the table. You could have very easily multiplied both sides of the whole problem by 3 and then gone from there. And your steps would just look a little different. This step actually would have been your first one, and then this would have been the last one. Okay? So either way is fine, and it certainly does not matter. That's it for Lesson 2.2, folks. I'll see you next time. Peace.